Hi, everyone. Thank you so much for logging on today for this session. We're very excited to have Adam here today from EKFB, and he's going to be talking a little bit about the railway lines and how they get built. So before we get started, if you or your students have any questions during the presentation, please feel free to throw them in the chat box, and we'll try to get to as many of them as we can at the end. Also, there's going to be a couple surveys that I'm going to throw in the chat box at the end that if you and your students could all fill out, that would be fantastic, as well as some polls. Before we get started, if you wouldn't mind just throwing in the chat box about how many students you have with you today so that we can get a gauge of how many people are logged on, that would be very helpful. And I'm going to hand it over to Adam to go ahead and get started.
Hi, everybody. Just to confirm, can everybody hear me? I'm guessing maybe just
You're good.
A nod or something like that. Excellent. I'm going to put an apology out first. I've made a good slide deck, but unfortunately, I didn't have time to go through the entire thing. So we'll just see how this works. But all in all, so I'm going to do a talk on HS2 today. And in this session, what we're going to cover, like for starters, what HS2 essentially is, the EKFB's involvement in that, what we essentially mean by high speed, the capabilities of HS2. We're then going to get some of I'd set some preliminary work, so we're then going to get your thoughts on why we're building this thing in the first place. And then we're going to look into some of the engineering elements that we need to uphold to maintain the capabilities of the railway, essentially. And then towards the end of the session, we'll have time for some questions. And there's an additional task for everybody, including the teachers and even my colleague. So before we go any further, I'd just like to introduce myself, if I can. 1 second, my slide deck has not moved on. So yeah, sorry, my apologies. I'd like to introduce myself. My name's Adam. I work for a company called EKFB. I've been working within the rail industry for less than a year. Prior to then, I was doing an integrated master at the University of Leeds, and that took me about 4 years. So I'm just going to pass you over to my colleague so he can introduce himself and tell you a little bit about himself.
Hello, I'm Ian. I'm a chartered civil engineer. I'm a little bit more experienced than Adam. I graduated with a degree in civil engineering 36 years ago. I've worked all over the world, and this is my opportunity to work with Adam and help pass some of that knowledge on to the next generation. I'm excited to see what we're going to talk about today.
Cheers for that, Ian. Anyways, so first of all, what is HS2? So it's a complete new railway network designed to connect the major cities within the UK. It's built within 3 phases. So we have phase 1, phase 2A and phase 2B. As you can see, phase 1 starts within London and terminates in Birmingham. Phase 2A starts in Birmingham and terminates in Crewe. And phase 2B is 2 independent legs that start from Birmingham, 1 to Leeds, and from Crewe to Manchester. But that's just basically, a bit of where it goes, essentially. So EKFB's involvement. So EKFB are covering an 80-kilometre section between these 2 red dots, which are indicated on this map, between Old Oak Common section, and that's a station, sorry, and the Birmingham interchange. As you can see, it's outlined essentially where it goes. So it's been Southam or Greatworth to Southam. That's my area, and it highlights the other areas there. I'm not really here to talk about what we're doing at EKFB. It's more a bit of a talk about what essentially high speed is and how we build that. So what do we mean when we say high speed? So it's a term that could get thrown around, and it's different from different transport networks. So essentially, it was first introduced in Japan. It was known as a Shinkansen, or what we call it in the West was the bullet train. And it, had capabilities of reaching 220 kilometers an hour, which is about 137 miles per hour, which doesn't sound fast by modern standards, but as a time, it was like a bit of an engineering marvel. But when we refer to high speed now, we're typically talking of speeds of like 250 kilometers an hour, which is about 155 miles an hour. So how does HS2 compare to that? Well, HS2 in theory, is capable of reaching speeds of 400 kilometers an hour, which is about 250 miles an hour. So for a little bit of context, that's faster than a Formula One car at a top speed or like a jet taking off at a runway. So it's pretty quick. So prior to this session, I set a little bit of preliminary work asking what your thoughts were. Basically, why are we building this? Now, there's obviously a bit of a clue in the title, High Speed 2, but I was just wondering if the teachers could give you a little bit of feedback, what some students might have put, if anything, not to worry if not, but just for a little bit of engagement. Did anyone put any? I don't know if anyone got the preliminary work. It was literally just asking what were your thoughts on why we might build a high-speed railway.
Teachers, if you want to go ahead and put that in the chat, that would be great. Thank you.
The only problem what I've got here is as my slideshow's coming up, I can't see the Microsoft Teams, so I do apologise for my inferior technical skills.
Adam, I'll field the chat and I'll let you know. You can then answer.
Excellent. Cheers.
So the first one is to replace the old track and go fast. And then it's to knock 10 minutes off the journey time.
Interesting.
Connect the UK.
Excellent.
Increase travel speeds and efficiency. New design, so faster, to help commuters travel to work quickly. And time is precious.
No. I'm waiting to talk. You could have done that during the tidy up time if you'd got yourself moving.
So one of our classes asked why keep building given the protests, and somebody has also said it's a vanity project.
Interesting stuff, and I'm ready to answer all these questions as well. Not turning it too political.
More people use the train, reduce pollution in cars, helping people get to work quicker, connects to major cities, less traffic on the motorway, less pollution, reduce car numbers, improve efficiency, more eco-friendly, waste of money given coded and working from home.
What an array of answers there.
Energy efficient, does the increased speed use more fuel to reach carbon zero? So I think there's a sort of two general themes there. One's about more efficiency and more speed, and one's about actually worried about the cost and the impact. Adam, makes.
So I'll go ahead and sort of answer the reasons for essentially why we're building this now. So the first obvious one is reduced journey times. The train goes faster than the current lines, so there's an incentive for individuals travelling from, Leeds to Birmingham, as this slide would indicate now, that the Leeds journey would be reduced from 1 hour and 58 minutes to 49. But that's just an incentive to get people to use the railway. The actual reasons are more on like a civilization-based aspect. So one of the major reasons we actually use is for capacity. So each one of these trains can carry up to about 1,000 people, and we can usually on a line put about 12 trains an hour, which is about 12,000 people an hour. That's a lot of people. And so while speed is an element to it, capacity is one of the major reasons for this. Our roads, our current infrastructure is overloaded. If you go on a motorway or something like that, you'll know if you hit busy times that there's a big capacity issue with everything. Like a capacity problem we have is hard shoulders on a motorway, for example, have been taken away and put for an extra lane. It's a sign of things being overfilled because of so many people. So that's one of the major benefits. Another benefit is freight. Now, you won't think about this, but your Amazon parcels don't just magically arrive somewhere. They come on these shipping containers. And those shipping containers currently get by via lorries. And they're on your motorways, and they again clog up your motorways. What we aim to do with this is by putting more people on a faster route, the current railways will be able to withhold freight services. They can't at the minute because current passenger travel is faster than freight. So it would essentially, this would block current transport. So we can't actually put freight on the existing lines. So this is another benefit. And as the slide says, we could take up to 1.5 million lorries off the road. Now, I know most of you don't drive cars who are watching this, but trust me, in 6-7 years time, this will be important to you. And there's another big thing. We can reduce emissions. These trains are fully electric. None of our train network in the UK is fully electric. That means we can power this thing on solar and wind energy alone. So we can literally power this from the environment. So we'll basically be able to draw us back to like carbon zero is what the aim of the game essentially. So those are like the four main benefits of building this project. Now I know it is controversial, but they had a very similar thing in Japan. It was very controversial when they built it, but once it was built, it was an engineering marvel, which everybody to this day is highly respected. Anyway, enough about that. So how do we build a high-speed railway? You know, so we know we need to build one. How do we go about building one? Well, I think first and foremost, as young people, it's important to understand the mechanics that limits us. So basically, what we are looking for on this train that can go 250 miles an hour is rider comfort. People essentially going to ride this train. It's not a roller coaster, as much as you guys might like it to be, and I would too. It's not it's not a roller coaster. It's a railway. And so what that means is, if someone puts a drink down on their table when they start the railway or in the train at 250 miles an hour, it can't fall over. It must be like a normal journey. So how do we uphold that? Despite the fact that we've got to navigate the landscape, which is full of hills and terrain that we need to navigate. So the basic principle that I need you to understand before this is nothing too technical. It's simply this. There's a radius in a circle, and the bigger the radius, the more gradual the curve. And that is basically all I need you guys to understand. And so basically when it comes to things like going up hills, which we'll let it go on now, it'll come into play in a second. But basically, we need to understand what the gradient of a hill means. Like, you know, so for every 100 meters we go across, high-speed rail is only permitted to go up or down 4. This applies in both directions, because going downhill one way means you're coming up the next. So you might think, why the hell am I talking about this? It's just going up a slope. But this means we are extremely limited to what we can do within high-speed rail. Essentially, now this might look complicated, but it's all about the radius, as I just explained before. If a train coming up a 4-degree or a 4% gradient is then coming down one, what distance does it need to cover in order to go from the up to the down? It has to go over a round area, because if it goes over a peak, like indicated here, it'd simply fly off the track. So we have to have this gradual slope that goes over here. So in order to satisfy what we said with the drink on the table, we would have to incorporate this curve. And that curve if we were to draw a circle through the earth, it would go down 50 kilometers. And it would essentially, from going up to down, would need a 4-kilometer stretch. That's quite big. Now, this isn't to scale. It is grossly exaggerated just to illustrate the point. But this slide indicates the actual tolerance that we would have. A high-speed railway cannot go steeper than that or lower than that. I've zoomed in there to show you the scale of a train and what 4 kilometers would essentially look like. So we have to keep these tolerances really, really small. It's essentially the closest thing to flat we can do. Now, same applies for a horizontal radius. When we're going around the corner, we also have to uphold certain parameters. Essentially, the radius for a circle, if we're going to do a complete circle, will be 8.2 kilometers. So we've got a little bit more tolerance, essentially, going horizontally, because what we can do, we can tilt the track. We can tilt the track over, which essentially pulls people in, but the force going around the corner pushes people out, so it balances it a little bit. What does 8.2 kilometers look like on a map? My apologies. If you're from London to Birmingham, this is what a radius. So this is the turning circle a high-speed rail would have to essentially take. So, I mean, you're probably thinking, why am I telling you all this stuff anyway? So the reason this is important is because as engineers, we need to understand that and conduct what we call feasibility studies. So we want to build a railway from London to Birmingham. How are we going to do it? Well, first of all, we need to know the limitations of a railway, which I've just illustrated there. And so there's many other factors that we need to consider, but those, as a young engineer, is probably the things that you need to be thinking about. And a feasibility study essentially weighs up your options. Now, it's not so much a task, but a bit of an exercise, but it's a bit of a play with some software that you might use as an engineer. You know, you might basically, so I don't know how it worked, but I told some people basically, or teachers, if you could download Google Earth, you could basically see, you can conduct your own feasibility on what we've just discussed. And a simple way of doing that is saying, right, okay, I'm guessing everyone can see my screen here, and I'm not just talking to myself, but
doing fine, Adam. Keep going.
Excellent. So we want to build a railway between London and Birmingham. Now that's a massive stretch of land, and it's predominantly filled with landscape, as you can, as the green areas will indicate. That is essentially landscape, and the grey areas are cities, towns, and everything else. So what we need to try do is we need to try go from A to B, and we need to try and navigate that. Really simply, you can just use in Google Earth, you can simply construct a path. So just say, I want to start here, and I want to start building my railway, avoiding, well, I've not done a good job avoiding the grey areas there, but avoiding all the grey areas until you have to get to the city. You can't avoid the grey areas in the city because it is a city and it's buildings. But what you can do, you can start to think, right, okay, this is the route I want to take. What might this look like, and what problems might this fit? What problems might we face? So if I just save this quickly, HS2, what we can then do using like essentially satellite imagery, we can show the elevation profile of this. So what this will do will give us, as I said earlier, we have a 4% slope to deal with, and we can't build a railway outside of that. So this clearly illustrates areas of, like, you see this here, for example, there's an area here of 10.8%. We can't build through that. What we'd have to do is devise this so we could try and potentially factor this out through many iterations of this. Now, I did set a little bit of a task. If you wanted to play with it, it's simply a play. You can literally draw some lines on here and try and literally factor out all these steep slopes and increments that we just can't deal with. One of the things that you do also have to manage is, if you zoom in, you need to try and avoid as much cities as you possibly can, town areas and everything else. This takes people a long time to determine. We're not going to develop a new railway in the next 5 minutes, but it'll be interesting if you could just go for 5-10 minutes, just have a little play and see what obstacles you might encounter. Now, I don't know how successful you were in downloading Google Earth Pro. I can literally run alongside you and just show you how easy it is to illustrate that. And another thing what you can do is you can fly along essentially the alignment and show what you would essentially encounter on the way. So this would just give you a quick run through and say, you know, the problematic areas that you might face. We ain't got time for that at the moment, though, because that'd take quite a long time, considering it's about 150 kilometers. But if you just like to go in your classrooms just to play around and see what you can essentially, if you can factor out all these, you know, these gradient areas here. I don't know if you might want to play, or if you manage to do it, or you can try do it as a classroom. If you downloaded it, I'm not getting much in the way of feedback here, so I'm kind of going blind.
Teachers, were you able to download it? If you wouldn't mind just putting that in the chat really quick so we know.
Not to worry if you didn't. Like, I can literally just run some on here, and it's a refinement process. What we're after. It's like, okay, this didn't essentially work. We'll try a different way, and it's like a feasibility. So again, we're just trying different options and ultimately trying to weigh out the best one that we've got, which will give us least resistance. I mean, for context, I'll just delete that. The best thing we could do is this. The unfortunate thing is, it probably won't work very well.
Yeah, Adam, if you wouldn't mind just kind of, for the teachers that weren't able to download it, just showing them kind of, you can do something with them, and then the teachers that did download it, you can feel free to go ahead and do the task.
Yeah, it weren't so much of an exercise as more of a play about, just to get some people thinking about, okay, we need to span this gap. How might we go about it? It's a long distance here, and we, you know, if you've ever done a motorway journey for 3-4 hours, we've got to try and build a railway that needs to be essentially flat through that gap. You know, so what you know, this is the exercise the others do at university. HS2 is one of the biggest infrastructure projects around at the moment, so they very had us conscious about HS2 essentially. And so we would do a lot of these studies and much on a much smaller scale typically as well. You know, you would typically be dealing with, you know, areas of, you know, this is probably, I'm guessing about 150 kilometers. You'd be dealing with much smaller areas and looking at the finer detail of the things that you need to avoid here. I mean, for example, we've just drawn a line across the country here. Look at the area where there's a housing estate there. You know, we're essentially cutting through so much of a city there. We'd have to try and factor that into the best of our abilities, but essentially it's not going to be something we're going to be able to cover in, you know, a 20-minute IT session. But that was just a play, and there's many other factors that we need to consider, but this, I think, is the biggest thing, and the thing for young minds to understand is that we are trying to navigate a landscape, and it's quite important that I'll just show the profile again. You know, we essentially need to eradicate this, because later on in the presentation I'll show what we can. Ultimately, it'll be possible to eradicate all the slopes, all the angles. It will be almost impossible to get rid of that. But I'm then gonna go through a few weapons in his arsenal, what we do to overcome that. I'm just taking a breather because once I get talking, I don't stop. So I'm just giving your ears a rest as well.
Teachers and students, if you have any questions, please, again, feel free to put them in the chat box, and we'll do what we can to get to as many as we can at the end.
As it would just essentially a play as well, I'll get back with the presentation, because it was it's quite a hefty task to try and take on in such a small amount of time, especially if you're not familiar with the software or don't have the software. So what I'll do is I'll resume to the presentation right at the beginning, unfortunately. So yeah, we were up to here anyway. So bearing in mind that it's probably impossible to eradicate all the slopes, all the hills in the way between such a large section. So I've just devised a simple engineering scenario which will just let us look about what we can potentially do, and as options when we encounter some sort of, I'd say, immovable objects, but nothing's immovable in civil engineering. So what I'm saying here basically is the gradient that we literally said we cannot go above because the train won't be able to operate at its capabilities. You know, a train's coming along here, and essentially we've hit a point where we can't overcome. Basically, there's no way around it. Just say we're hitting a region of hills which are almost, you know, impenetrable for a region. This is essentially simulating that. So we've come across a gradient. What are his options? Well, as first option, what we might consider is we could essentially reduce this hill by spreading it out. One of the ways we could do that is by introducing a viaduct. A viaduct would essentially let us, you know, take that gradient a little bit of a slower rate, allow us to reach the peak, and then come down the other side. This is one of an illustration of one of the viaducts at Wendover Dean. It's not yet built. This is a computer generated image, but this is what it will look like on completion. Now, this is one of his options, but depending on the distance of this gap, you might have quite a large viaduct that might be unnecessary. So another option what we could have is we could tunnel. We could simply build a tunnel through this mountain or through this hill, and you know, it goes on for a much lesser distance. Now, there is some problems with tunneling. It's typically expensive because you have to excavate all this material out and put it somewhere, and that can be quite problematic at times. But one of the things with HS2, what we're trying to do is literally we're going to try and cover it up, because not many people want a high-speed railway running through the background. So we're going to do our best to cover it up. So we're essentially implementing tunnels wherever possible, just to try and, you know, contain HS2 essentially. So with tunneling, there's two types of tunnels. There's what we call green tunnels and there's bore tunnels. Green tunnels are when what we want to do is it's a shallow tunnel. So what we're going to just cut an area out of the landscape, like a big V, and we're going to put a railway in it. All the structures that we need to contain, the kind of cylinder, like a pipe. It's almost like digging out of the ground and putting a pipe in it and then covering it back over. And that's as tunnel. The other option is what we call a bore tunnel, is what you can kind of see in this image here, which essentially like it's too deep. It's not effective to start cutting out of the land. What we have to do is essentially drill holes through the landscape. It's not the most cost-effective way, but when you need to maintain the land above it and it's not cost-effective to dig like that, this is what we have to implement. So we're implementing over about 30 miles worth of tunnels across the project, which is absolutely enormous. Like, and in total, we'll probably be dealing with about 60 miles of like, you know, tunnels or cuttings all in all. And what does that even look like? You just think it's like pulling out mud or anything like that. We have to move 130 million tons of earth, which is enough to fill Wembley Stadium about 15 times. This is absolutely, what we're doing is absolutely mammoth. So there is additional factors that we could have considered in this presentation. The geology, the habitats, the water. There's so much that you need to consider when you're building this. You know, from university coming to here, my perception of what we need to build a railway has changed so much because of the endless complications that might arise. I was only talking yesterday with a colleague Ian about the geology. If you go over soft ground and it's clay and you go a high-speed trains emit seismic waves. It's like an earthquake, essentially. It's so powerful. And what that will do is essentially vibrate the track so much and destroy the track it sits on. So what we're looking for when we assess the ground is firm ground. And if we can't get firm ground, we have to put serious feats of engineering in the ground to make sure it stays stiff. There's other things that we need to consider. Habitats. Habitats are so important. We have endangered species on the line, and it's very important that we make sure that they remain alive, essentially. You know, we have bat habitats and various other animals that we need to consider. And there's also water. I don't know nowhere near as much about water as what Ian does, but essentially when you dig below the ground, there's a groundwater. And basically we can't, you know, it's essentially like putting a pipe or a railway through an ocean once you get so deep. We have to try and manage where we interact with the water. And not only that, the water is what we drink. We need a good supply of water, essentially. So it's very important we don't contaminate that. Basically, that is the end of the presentation I have. You know, if you have any questions, any questions whatsoever, by all means, fire them at me. If you have none, I have a little task for the teachers and whoever wants to take part, which might be just a little bit of an entertaining way to end this.
Yeah, Adam, it's up to you. We have a few questions in the chat. If you want to take a few minutes and answer those.
Yeah, I can't see the chat at the minute. Ian, could you read the chat just because the slideshow is kind of blocking my perception of Microsoft Teams?
Yeah, I'm busy trying to answer them by text as I'm going. There's an awful lot of them. Like I've just done a very long one about how the protesters are dealing with it. So I put an issue about the environmental protesters, etc., in the chat.
One thing
just to explain where we sit in the process as well. I'm not delivering the project is in 3 bits. There's an initial contract with it's called an enabling works contract. There's then another contract which is a civil engineering contract, which is our contract, and then after us there'll be another contract after we've finished that'll actually install the tracks and all the overhead catenaries and all the electrical supplies. So we're the middle of we're like a sandwich between 3, and so we most of the protester interaction is with the enabling works, the first contractor, because they're the ones that's on site first. They're the ones that's actually knocking all buildings down, cutting a lot of the trees down that are required, and they're also the ones that's moving old churchyards, and quite a lot of the archaeology is done by that. We pick up from them and finish off anything they've finished, and we move forward. There's a lot of questions on train power. Train power it's not going to be battery. It's going to be powered from an overhead catenary system. So there's an overhead wire that runs the full length of the 80 kilometers, and the train picks up the power by in the same way as a tram might, with a connection that travels with the train. And how did you become an engineer, Adam? You can answer that one.
It's an interesting story, and it's not the conventional route. I didn't leave school with particularly good GCSEs or A levels. Actually, I actually left to be. I was an electrical apprentice, and I lost my job, and then I went to move to Australia temporarily, and I found that their industry, mining industry, was thriving quite well. I worked out there for 2.5 years in mining and construction, and decided that whilst doing back-breaking work paid well over there, it wasn't going to be the future for myself. So I came back to the UK and decided to do a foundation degree in maths, physics, and chemistry. That took a year, and then I did 3 years bachelor's to get me my degree, and I incorporated in that was an additional year to do a master's. Now, it might sound a long time, but when you get a little bit older, you'll realise, it's not such a big deal, and university is great fun. So yeah, that's how it's got me here. Ian is actually my boss. He got me this job, and he's been very crafty, because he was meant to deliver this speech, but he took a holiday last week. So the burden of this presentation lies on me. But it's okay. I've got a task at the end, which I hope to get him back on. So.
I'm going to say it's interesting because I did maths, physics, and chemistry at A levels, and I did a degree in civil engineering. And it's an interesting thing because I'm slightly older than Adam, and my daughters looked at what I've done through my career and liked what I did so much. My daughter has actually decided to become a civil engineer as well. So she's just finished her master's degree in civil engineering and was actually working on HS2 for a period of time. So she's so excited by the ability of engineers to change the place we live, and the creativity that we need to actually do the engineering, and just the sheer scale of what we can do. She's decided that this is what she wants to do for her life going forward. So I'm really pleased that I've been able to enable her to take that step. We don't have enough ladies and women in engineering. So if there's any girls out there that wants to come, please come and join it. It's a great profession, and you'll have a really stimulating time.
I will just sort of add to it, this is one of the biggest types of engineering. Civil engineering, it stands for civilization engineering. And so while HS2 will have its protests and the people won't like us, what we're doing now, in the future, what we will build now will be essentially, it'll be a fundamental part of society. People use this. It happened in Japan in the 60s. Well, the people who designed the railway, essentially, while it was being built, were hated. Why are you spending this money? It doesn't make sense. Someone high up in the railway industry even referred to it as madness. Years later, it became this absolute epic feat of engineering that is still regarded as one of the best things they actually built today. We are literally embarking on our own project, and we're in the exact same stages that those engineers were initially in. If you become a civil engineer, you really are taking in something that will really change the world. So, but I don't know if there's any more questions. I ain't got the chat box.
So there's some more. So how does the ground stay firm, keep it sturdy enough when putting a tunnel in? So Adam's talked about how we put tunnels in, one of which is this board, one of which is a cut and cover. So a bored tunnel has what's called a tunnel boring machine, which is a very large screw, effectively, that's just drilling its way through the earth. If the as the tunnel boring machine goes through, there's a concrete liner put in behind it. And that concrete liner holds the roof up effectively. In the tunnels we've got, they're what's called a cut and cover tunnel. So we dig, it's built very much the same way as the London Underground lines were built in the 19th century, where we're actually taking material out. So we'll dig a big trench, and then we'll put effectively a very large pipe in and backfill around that very large pipe. So the very large pipe holds the earth up, and that will actually satisfy everything. Engineering, from an engineering perspective, is the most economical way of creating a tunnel. I think I've explained about the environmental integrity part of Adam and I's day job. We're not. This isn't our day job of presenting to children. Our day job is actually to go and build this railway. But what our role is actually very much about making sure we comply with all the environmental limitations. So we regularly speak with the Environment Agency, Natural England, lots of planning authorities to make sure that we are the best neighbour we can potentially be. Somebody's asked whether a pulley system could be done this. There is actually a pulley system. It works it won't go the speed we need it to go at. So you'll find that places like aircraft, the train that goes between aircraft terminals, quite a few of those are on pulleys, and they're very, very, very robust. As far as I'm aware, the rolling stock contract hasn't been yet let, but I think it's going to be with a driver in it, but all the signalling will be done via signalling in the cab. So there'll be a series of electronics that will actually give the signals in the cab. There are very few stops, because every time you incorporate a stop, the train's got to slow down. So there's a long period of time for this train has to slow down to get to a point where it stops. There's an amount of time it sits at the station, and then it's got to speed up again. And if you have too many stops, the whole advantage of the speed is lost. So there are actually very few stops. In fact, in our area, there are no stops at all. And that causes some problems because the local people don't necessarily get any benefit at all from this. So the people we're working closely with, there is no benefit. They can't get to London or Birmingham any quicker than they can at the moment when we're finished, but they have to put up with the disruption. All the concrete, our concrete's going to be built in the tunnel linings, in the bridges, and potentially on the track slab that Adam talked about. So where the rails sit. You can't sit, normally you'd sit rails on a what's called a ballasted section, but because this is we need the levels to be so smooth, we have a concrete slab that the track sits on. And will this ever go worldwide? Part of the HS2 is going to link to HS1, and eventually, I mean, even now you can take a train from London and you can travel by train without getting off all the way to Paris or to Brussels, and shortly you can go to Amsterdam without getting off the train. And in the fullness of time, you could potentially get on a train in Manchester and get off in Amsterdam. And it would save, it's a much more economical and environmentally friendly way of getting from Manchester to Amsterdam than flying potentially.
I was just going to say, Ian, we've got 2 minutes left. I don't know what the rate of questions. Will I have time to do this task? I'm kind of
go and do your task, because you want to set me a task, Adam.
I want to set you a task, and I want to see if someone essentially can beat you at this task. So I apologise if there were more questions. Literally, you could answer questions all day on this subject. So there's a bit of a final challenge, and I think it's got to be taken part as classrooms. And you know what? I think the teachers can get involved too. And, you know, if you beat my boss, you can have his job. So basically, I saw this on a YouTube video, and I think it gets your mind working as a little bit of an engineer, and the kind of the maths you need to start thinking about. It's not overly complicated, but the pressure might mean lead you to a wrong answer. So I'm going to play a video that I saw yesterday, if it loads, and essentially it's a maths question. So you might want to have your pens and pencils ready, and basically it will be, if I can actually play this. Whoever gets the right answer the fastest, that you win. Right, I'll play it again because I appreciate that's a pretty heavy question, but if you can get an answer to the fastest person to get an answer to me.
It's a little hard to hear, Adam, just so you know.
Oh, right, okay, my apologies. Is the sound coming through the speakers?
No.
Ah, right, okay. So what I'll do, I'll explain the question. It's what, sorry?
It does look like we're just out of time here, though. So
That
I
was
don't
my,
know if
that,
we'll get a chance to complete this.
yeah, not to worry anyway. I'll just have to leave you on that that cliffhanger there.
Thank you, Adam, and thank you, Ian, so much for being here. Thank you, students. The participation has been amazing. Teachers, I've gone ahead and put some polls in the chat. If you could just answer those polls for whatever the majority of your students vote, that would be really helpful. And then go ahead and fill out those feedback forms I posted as well and send them to your students to complete later on. So again, thank you so much, Adam and Ian, and thank you, students and teachers as well.
Thanks, everybody. Really appreciated your attention there. It's much appreciated.
Thank you. Bye now.
See you later, everybody.